Hello, AP Calculus students of the future. It's Mr. Ford with another summer packet tutorial. Another important one that shows up all the time in the AP Calculus. In fact, these are often questions on the AP Calc test. Only one or two, and they're usually pretty simple, but they often are here. Asymptotes. So we'll draw a quick picture really fast about some things in review before we jump into this, but let's think about what's going on here. Usually, when it comes to asymptotes, you'll see a graph that looks maybe something like this. Maybe you have a vertical asymptote like this, and maybe you have a horizontal asymptote like that. So an asymptote is defined as an imaginary line that a graph approaches but never touches. Well, never touches, I don't really like that language because you can have asymptotes that a graph does go through on its way to being asymptotic with it, but a vertical asymptote would look something like this. I usually abbreviate a vertical asymptote, and I will on this video, as VA. And a horizontal asymptote I will abbreviate as HA, like that. The only other thing we got to mention here is that it's also possible that a graph like this might have a hole in it. And we'll talk about when that will happen and why that happens. But we will also have to be aware that holes can happen on these graphs. A vertical asymptote happens at any point when you have, let's say, x minus 2. Since plugging in 2 into this function would cause the graph to not work, 2 minus 2 is 0, you'll have a vertical asymptote at x equals 2, this vertical line right there. A hole would happen if you had something like, let's say, x minus 4 over x minus 4, where that 0, or that thing of x equals 4, that causes 0 on the bottom of the fraction, but it also causes 0 on the top of the fraction. So there is an error. You cannot get an answer there. 4 is not in the domain of the function, but it doesn't cause the graph to do anything funny because it cancels out with the behavior on top, basically. Horizontal asymptotes will take a little bit longer to explain, but we'll see some examples of this. Let's get into it. All you really need to know is what we're looking at in these problems is the bottom of the fraction, really. When the bottom is equal to 0, there's going to be a vertical asymptote. And so that's going to happen with number 1 at x equals negative 5. My tablet seems to be running a little slow right now, so I'll try to be a little more patient with it. I'm asking a lot of it right now. X equals negative 5 will be a vertical asymptote in this problem. Now, as far as horizontal asymptotes go, what we want to think about here is what's called end behavior. I'm always wary to introduce calculus notation because there's a bunch of new ideas in calc that you have not seen before. So I won't introduce them in this video. But what you might think about is what happens as x approaches infinity. If you plug in very large values of x, what's going to happen here is that these x's are going to grow to infinity at the exact same pace. There is a minus 1 on top, and there is a plus 5 on bottom. So they will be different numbers. That's important. But they are going to be, in the face of infinity. Infinity minus 1 and infinity plus 5 are both infinity. So it's important to understand they're not the same number, so they're not going to be 1. But these are going to approach 1. So I think y equals 1 is your horizontal asymptote, like that. This also happens when x approaches negative infinity, but we'll talk about that in other examples. Okay, so let's take a look at number 2. So in this one, there is going to be a vertical asymptote at x equals 0. That's pretty easy to point out right now because plugging in 0 on the bottom makes it a problem. As far as the horizontal asymptote, again, what you want to think about is what's going to happen as x approaches infinity, as x gets larger and larger. This number on the bottom here is going to be approaching infinity and then also being squared, which is going to make it approach infinity even faster. And we're going to take 8 and divide it by infinity. That's going to be 0. And it's 0 if you go to infinity on the right, positive, and also on the left, negative. Plugging in negative infinity also gives you positive infinity and also gives you 0. So y equals 0 is your horizontal asymptote in this problem. Again, the challenge of this packet is to do as much of it without graphing as possible. I don't even have a graphing calculator with me in the studio, so I won't bother with it. Okay, number 3 is going to bring up the interesting case. What's important in this problem is that we should factor the top of the fraction first into x plus 8 times 2. And this will bring up the example I was kind of mentioning a minute ago. In this case, what we have is x plus 8 over x plus 8. So there is something happening when x is negative 8, although This graph will not have a vertical asymptote there because those factors basically cancel each other out. In fact, this graph, if you were to graph it on a graphing calculator, it will be the line y equals 2. You will see a horizontal line. It will go through 2 on the y-axis and continue forever. And it's only unless you look at the table of that graph that you will see that at x equals -8, there is a hole on the graph. Oh, my battery's running low. Oh, I might want to plug in? Well, allow me to take care of that, friend. That might be why my thing is running a little hot. Okay. Oops, I hit the drum set. Let's see, where's the battery port on this thing? There she is. Boop. Okay, we're in good news now. There we go. Now we're in shape. All right. Okay, now the real juice. Okay. So anyway, there is no vertical asymptote on this one. But there is a hole at x equals -8. You will not see that on the graph. Even if you graph it on Desmos. I don't think Desmos shows you holes. You have to click on it and say, oh, -8, there's nothing there. Now, as far as the horizontal asymptote goes, kind of draw a line there. Again, we want to think about what's going to happen as x approaches infinity. As you approach infinity, again, it's all going to come down to 2x and x because plus 16 and plus 8 don't matter in the face of infinity. But there is going to be a 2-to-1 relationship between the top and the bottom of the fraction. And as you race to infinity, on the top, 2 divided by 1 is going to be 2. So there's going to be a horizontal asymptote at y equals 2. And that will also happen on the left side if you go to negative infinity. So we'll see some more examples that will help make that horizontal asymptote thing a little more clear in a minute. For number 4, now this one's going to require a little bit of factoring. So let's factor things first as best we can. On the top, we'll pull out a 2x, it'll be x plus 3. And on the bottom, we'll factor that into x plus 2 times x plus 3. You know, nobody's requiring you to be that good at factoring, but you know, it's one of those things, the faster you are at it, the more effective you get to be. So this is a timed AP test you're taking after all. So it's in your interest to get like snappy at things, you know? So as far as our vertical asymptote, there's going to be a vertical asymptote at x equals -2. That will cause the bottom of the fraction to be 0, and that is not repeated on top. There's going to be a hole at -3. Because that will force a 0 on the top and the bottom at the same time. So this graph will resemble the graph of 2x over x plus 2. You won't see the x plus 3 behavior at all, but you will see a hole at -3. As far as vertical asymptote goes, now again you want to focus on the leading coefficients. Again, all of these numbers, 2x squared, 6x, x squared, and 5x, all go to infinity as x goes to infinity. But here's the trick, is that x squared goes to infinity faster than 6x and 5x. And in fact, in the face of infinity, nothing else matters except for these two guys, which just like in the last problem, have a 2-to-1 relationship. And that will continue to happen as they race to infinity, and 2 over 1 is 2. So there's a horizontal asymptote at y equals 2. Again, positive and negative. Number 5. Again, you might recognize this factoring scheme on the bottom as x plus 5 times x minus 5. That is a difference of squares. We saw that in the last video. I think this exact same problem, actually. No, it was 36. Doesn't matter. So we're going to have 2 vertical asymptotes in this one. X equals 5 and x equals -5. There are no holes because that 0 is not repeated on top and bottom. Now, as far as the horizontal asymptote goes, here's a pattern you want to be aware of. As x approaches infinity, x goes to infinity and x squared goes to infinity, but x squared goes to infinity faster than x, and so the bottom of this fraction will always be infinitely more than the top of this fraction, even though they're both going to infinity. That's a really big key mathematical concept, but the bottom line is you're going to have a number on top that's not nearly as big as the number on bottom, and so as those numbers continue to increase, you're just going to be dividing a small number by a huge number, and that's going to give you 0 every time. There is kind of a pattern here if you're picking up on it. We saw it in the problem right up above in number 2. If the degree on the bottom is bigger than the degree on top, you're going to be going to 0. Doesn't matter. If the degrees are the same, as we saw in problem number 1, 3, 4, and again we'll see in 6, then you have to divide the coefficients to find out where that horizontal asymptote will be. We'll talk about that in this problem right now. The top of this, by my knowledge, cannot be factored. X squared minus 5. I mean, I guess you could split it up into plus square root of 5 and plus minus square root of 5, but why would you? That's not going to help us at all, and those factors will not be repeated on the bottom. So I'm going to leave the top alone, x squared minus 5. On the bottom, though, you can factor out the 2, and it's x squared minus 6. And, you know, that can't be factored either, so I guess this isn't honestly all there is. There's a cat in the roof. I don't know if you guys can even hear that in the video. This studio is not very soundproof. Anyway, what we should do is look at the bottom of this fraction and figure out when does x squared minus 6 equal to 0. And that's going to happen when x squared equals 6, and that's going to happen when x is equal to plus or minus the square root of 6. Since those zeros are not repeated on top, those are your two vertical asymptotes. So you have vertical asymptotes at x equals the square root of 6 and x equals negative square root of 6. There are no holes on this graph because none of those zeros are repeated in either case. And the horizontal asymptote, again, we're going to match up the behavior of x squared and 2x squared. So again, as for your horizontal asymptote, as x approaches infinity, what does y do? Again, x squared, they're both going to race to infinity at the exact same rate, but there will be a 1 to 2 relationship. So just like how number 4 was 2 over 1, this problem over here in number 6 is going to be 1 over 2. So we're going to say y equals 1/2 for our horizontal asymptote. Hopefully you're getting the pattern of this. These are pretty easy problems once you get the hang of it. I'm taking some time to explain it right now, but let's look at number 7. 3 more to go. Okay, so number 7 is going to bring up an interesting case where the degree on top is bigger, so let's talk about that. First of all, let's break it down into, on the bottom, no, nothing factors in the bottom. You cannot factor x squared plus 4 into anything reasonable. So actually, if you think about it, this one doesn't really require any pre-work. You just got to think about things. The bottom of this fraction is never 0. If you think about it for a minute, you'll see what I'm talking about. X squared is always positive. Always positive. And then from there, you're going to add 4 to it. The smallest thing x squared can be is 0. So the smallest thing the bottom can be is 4. This is never 0. So there is no vertical asymptote. There's no holes either. Nothing makes the bottom 0, so there can't be a hole or a vertical asymptote. This is completely continuous, we might say. As far as the vertical asymptote, there's not one of those either. And the reason why is because if you start plugging in, if you say, well, this is actually a lot more complicated question to answer in this problem than it is in other problems, but I'll do my best to explain it without getting into a super amount of detail, because I suspect we'll be going into this in a different video. But as x approaches infinity in this problem, x to the third power goes to infinity, and x squared goes to infinity. But as we discussed earlier, x to the third goes to infinity faster than x squared. And that means that the number on top is going to be way bigger than the number on bottom, which means that y is also going to go to infinity. There is no horizontal asymptote in this one. There's no asymptotes at all, which is a good point to bring up. Not every graph has to have one of these things. In fact, it would have to be a fraction, or what we call a rational function, where you have a top and a bottom to even have a hole or an asymptote in the first place. All right, let's jump into number 8, which I suspect is going to be kind of a pain. Let's see. We got to start by factoring this quite a bit. I was thinking that the top might be one of those difference of cubes things we talked about a couple videos ago, but it's not, because it's not a difference or a sum or of cubes. But we can factor an x out, so that might be important. X squared plus 4, as we mentioned in the last one, does not factor to anything. On the bottom, well, we can kind of use that tricky trick thing we did in the last video also. I see that x to the third and 2x squared both have an x squared involved, so we'll factor that out, x minus 2. And these guys also factor out a 4, and you get x minus 2. That's nice. And so what we've got here is we have on the top x times x squared plus 4. On the bottom we have x minus 2 times x squared plus 4. Pretty groovy. Cool. Okay, so what does this mean for us in our problem? Well, we have a horizontal, a vertical. I always get these mixed up when I'm doing these problems. When it comes to vertical asymptotes, I'll use a colon for this. Vertical asymptote. Well, x equals 2 is one of them. 2 makes the bottom of the fraction 0, and it does not make the top of the fraction 0, so it's a vertical asymptote. X squared minus 4 is interesting. It's on the top and the bottom, but it does not create a hole because x squared plus 4 cannot be 0. So I don't think it does anything. In fact, you could probably cancel it out of this problem, and nothing would change at all. So there's nothing there. As far as the y-axis goes, or y-intercept goes, horizontal asymptote, let's think about this for a minute. Again, as x approaches infinity, as x gets very, very large, what does y do? Oh, well, if you look at the leading coefficient, just like the last couple times, you have x to the third, x to the third. Again, all of these x's go to infinity. X goes to infinity, x squared, x, they all go to infinity. But x to the third goes there faster. That's the reality. X to the third goes to infinity faster. And there you go. So what that means is that you're always going to have a one-to-one relationship because the coefficients are both 1. So y equals 1. You just divide the coefficients. It's going to be 1. And let's look at one more. Number 9. This one, let's see. Let's go ahead and do a lot of factoring. We had kind of the same. Is it the same? Oh, it's the exact same bottom as the previous problem. Oh, cool. We can skip a lot of work on this one then. I love when they do that to us. We'll factor a 10 out on top because x plus 2 is going to be important. But we already know the bottom of this one because it's exactly the same as the previous. Oh, it's not. It's so freaking close, though. Oh, what's the only difference? This one's going to be... Okay, I suppose we'll go for it. X squared times x minus 2 minus 4 times x minus 2. Yeah, okay. So this is on the top, 10 times x plus 2. On the bottom, it's x minus 2 times x squared minus 4. Again, taking the x squared and the minus 4 and putting those together. But then that itself can also be factored. Oh boy, this is lots of fun. So x squared minus 4 is a perfect square trinomial. So it can be factored into, let's leave x minus 2 to the side. That can be factored into x plus 2 and x minus 2. Okay, there we go. That is the perfectly factored version of this problem. Okay, now that we got it all factored, we can start thinking about things like asymptotes. So let's talk about vertical asymptote first. Zeros that are only on the bottom of the fraction. X equals 2. That will make this and this equal to 0, and it does not make the top equal to 0, so that is the only vertical asymptote. There is going to be a hole at x equals negative 2. Because plugging in negative 2 will make the top and the bottom 0 at the same time. And when it comes to vertical asymptotes, let's check our leading coefficient. Oh, it's not even going to... Oh, my cat fell through the roof just now. Do you see her? There she is. Say hi, Bonnie. She just showed you her butt. That's her saying hi. So, the top here is 10x, and the bottom is x to the third. Again, the big idea here, there's a big calculus idea that we're kind of dancing around right now, is that the x to the third will always trump the 10x. And so this is just going to go to 0, because they're going to have a small number divided by a huge number. So it's going to be 0. So there is a horizontal asymptote at y equals 0. There you go. And let's take a look at number 10. These assignments tend to end with a trickier problem, so this is no exception. Number 10, hint expressed with a common denominator. So this is another thing that we're kind of like, well, I sure hope my calculus students know how to do this. But I hate to be that kind of guy because I don't want to gatekeep anybody from this class. I just want to make sure that you can do this. If I can do it, you can do it. That's the attitude. So let me show you how I know how to do it. Usually what you want to do is you want to take both these terms and multiply by the denominator of the other term over itself. Let me just show you. Like, for example, take 1 over x and multiply it by x plus 2 over x plus 2. Essentially, you're multiplying it by 1, which is why you're allowed to do this. We'll keep our minus sign there from the original problem. And we have our x over x plus 2, the other term. This one we're going to multiply by x over x. So with some highlighters here, I'm taking the denominator of each term and multiplying the other term by that thing over itself. That's kind of what's happening here. What's going to happen is that's going to create a common denominator. We can then combine these two things into one thing that we can then analyze the same way we've been analyzing the other ones. So the first term becomes x plus 2 over x times x plus 2. And the second term becomes x squared over x times x plus 2. And now we can add these things together. This is negative x squared plus x plus 2. I changed the order around a little bit. Now, as far as the top of this fraction goes, can we factor it? That's a question that is probably worth at least thinking about for a minute. I mean, I would guess that if we're going to be able to factor it, I would guess that one of the factors is x plus 2. Well, it would have to be negative x and positive x. It would have to be 1 and 2. Let's see. Yeah, I think plus. Would plus 2 plus 1 work? Hang on, I'm just thinking of this one. That would give me negative x squared plus 2x plus negative x plus 2. That's the one. That factors. But thankfully, or I guess, I don't know, not thankfully, nothing on the bottom is repeated on the top. So, I mean, that's it in its most factored form. All right, let's answer the question then. Horizontal asymptote. Or sorry, vertical asymptote. Oh, jeez. Vertical asymptote. This is going to happen. I see two of them. X equals 0 and x equals negative 2. Those are both going to force the bottom of the fraction to be 0 and the top will not be 0. I do not see any holes happening, no zeros repeated on top and bottom. And as far as the horizontal asymptote goes, this is a little tricky to see, but let me actually expand it out here. Let's take a little side step from this step. We have negative x squared plus x plus 2 over, let's actually expand it. It would be x squared plus 2x. Now, what you got here for your leading coefficients, you got negative x squared and positive x squared. And again, as x goes to infinity, we'll write that down, that's important. As x approaches infinity, those both go to infinity at the same rate. However, the one on top is negative and the one on bottom is positive because that negative sign is attached to the end of this thing. So you plug in infinity, you then square it to become infinity squared, and then you make it negative. So it's negative infinity squared over positive infinity squared. That's going to be a negative 1. So y equals negative 1 will be your horizontal asymptote. There you go. So, again, this one is, I hate to, again, I've said this a lot in these videos. You hate to use the word expect or should. That's not the language I mean to bring to a class that's already pretty demanding. So I'm hoping by doing these and walking you through them, you're starting to feel like, I could have done that on my own. I could have seen where that answer came from. That's the spirit. That's where I want you to be. I want you to look at an answer guide and be able to go, oh, I could have done that. I do that all the time when I'm doing stuff, doing math problems. I'll look at the answer and go, oh, I see how I could have figured that out. That's exactly the spirit you want to have going through this class. I want to approach calculus with the attitude that you could have discovered this. If you were Isaac Newton living in the 1700s with a rudimentary understanding, you could have figured this out on your own because somebody did. That's exactly where all math has come from. Okay, hey, thanks for listening to me ramble for another 23, 24 minutes. I'll see you in the next video. Go outside, do something fun.